Hello everyone, and welcome to this in-depth tutorial on conducting a complete propeller analysis using the latest version of Ansys Fluent. In this video, we will be taking you through the entire process, step by step, ensuring that you gain a thorough understanding of the procedure. Whether you're a beginner or an experienced engineer, this guide will help you perform accurate fluid flow simulations for propeller performance evaluation. Before we begin, ensure that you have Ansys installed and set up correctly. Also, familiarity with Ansys Workbench, Fluent, and Design Modeler will be beneficial. We will walk you through the process from setting up the geometry, meshing, and applying solver settings to obtaining useful results and visualizations. This detailed breakdown will ensure that you can conduct your own simulations efficiently and interpret the results correctly. Now, let's get started. The first step in our analysis is setting up the project environment. Open Ansys Workbench and select Fluid Flow, Fluent. This will create a new analysis system. If necessary, you can rename your project for better organization. Next, right-click on Geometry and select Edit to open the Design Modeler. This is where we will define the computational domain for our propeller analysis. The computational domain is essential as it represents the volume where fluid flow calculations will take place. Properly setting up this domain ensures accurate and meaningful results. Once inside the Design Modeler, the first thing to do is set the appropriate measurement units. Navigate to the Units tab and select millimeters, as we will be working with metric units for consistency. Now, we need to create an enclosure around the propeller to define the fluid domain. Go to Tools and select Enclosure. This enclosure represents the space where the airflow around the propeller will be analyzed. The enclosure should be large enough to capture all relevant aerodynamic effects, but not so large that it increases computation time unnecessarily. The next important step is to align the propeller along a specific axis to ensure the simulation is set up correctly. In our case, we align the propeller along the x-axis because we want the airflow to enter from one end of the propeller and exit through the other. For the enclosure, define a cylindrical region that represents the primary study area. Provide appropriate dimensions based on the propeller size, ensuring that it is sufficiently large to capture airflow effects. A well-sized domain allows for better resolution of flow behavior around the propeller. After defining the cylindrical enclosure, create a second enclosure using a box shape and name it Surrounding. This surrounding enclosure acts as the outer boundary of our simulation. The dimensions should be sufficiently large to allow for an accurate simulation. Typically, the values are plus x-axis 800 millimeters minus x-axis 50 to 60 millimeters. Other axes adjust accordingly. Next, we need to remove unnecessary parts of the geometry to create a clean simulation domain. Navigate to Create and select Boolean. Perform the following Boolean operations. Subtract the inner rotating region from the surrounding enclosure while keeping the tool bodies. Subtract the propeller from the rotation region, but do not keep tool bodies. Once these operations are complete, generate the final geometry and exit the Design Modeler. Now that the geometry is set, we need to generate the mesh for our simulation. Right-click on Mesh and select Edit to open the meshing module. The first step is to enable sizing to refine the mesh and ensure better accuracy. Click on Mesh and go to Sizing, then select Yes to enable refinement. Generate the mesh by clicking Generate. This will create the computational grid that Fluent will use for numerical calculations. Next, we must define boundary conditions by selecting specific parts of the geometry as named selections. Right-click on different faces of the enclosure and create the following: Inlet, the entry point of the fluid. Outlet, the exit point of the fluid. After assigning these named selections, update the mesh and exit the meshing module. Now, we move to the Fluent setup. Right-click on Setup and select Edit to open the Fluent solver. First, check the double precision option. This increases computational accuracy, especially for cases involving fine details in turbulence modeling. Next, select the number of processors based on your system's capabilities. Using 2 processors is a good balance between speed and resource usage. Once inside Fluent, the first step is to verify that the mesh is properly imported and conforms to expected quality metrics. Navigate to the viscous model settings and choose an appropriate turbulence model. For our study, we select Reynolds stress model, which captures complex turbulent interactions more accurately than simpler models. Go to Cell Zone Conditions and select Rotating Region. Enable Mesh Motion and set the angular velocity to revolutions per minute, RPM, with a speed of 500 RPM. Define the rotation direction. Since the propeller is facing along the x-axis, set x equals 1 and z equals 0. In boundary conditions, change the inlet type from velocity inlet to pressure inlet for better control over pressure variations at the entry point. To ensure numerical accuracy, go to Methods and refine the numerical schemes. Set turbulent kinetic energy, dissipation rate, and Reynolds stresses to second-order upwind. This improves stability and accuracy in solving turbulent flow equations. Next, navigate to the Initialization tab and choose Hybrid Initialization. Click Initialize to prepare the simulation. In the Run Calculations section, set the time setting to steady time for laminar flow conditions. Adjust the number of iterations as needed to achieve convergence. Run the simulation and allow Fluent to compute the results. Once the simulation is complete, we proceed to analyze the results. In the Results section, create a plane using Location to visualize cross-sectional data. Generate contour plots to examine variables such as pressure and velocity. Select the previously defined plane and specify the number of contour levels for better resolution. To analyze airflow behavior, generate streamlines. Select From Inlet. Set the number of points to 300 to capture flow details accurately. Run the analysis to observe the final results, focusing on pressure distributions, velocity fields, and turbulence patterns around the propeller. Congratulations! You have successfully conducted a propeller analysis in Ansys Fluent. This tutorial covered the entire process, from setting up the geometry and meshing to running the simulation and interpreting the results. By following these steps, you can optimize your propeller designs, analyze performance characteristics, and refine aerodynamic efficiency for better results. If you found this video helpful, don't forget to like, subscribe, and leave a comment below. Stay tuned for more Ansys tutorials and CFD simulations. Thanks for watching, and see you in the next video.